What's poppin', dogs? Mr. Allen here, about to have an absolute blast in this video, graphing absolute value functions. And we're going to describe the transformations from that parent function, f of x equals the absolute value of x. Just a refresher real quick on our parent function, we're going to have a graph that starts at the origin like that, and then it just goes up 1 over 1, up 1 over 1, and makes a V shape because the absolute value of -1 is +1. Absolute value of -2, if I input -2, I get +2. And we get this V-shaped graph like this. So then what's going to happen with this other graph here? I'll do it in pink now for this one. We have x plus 2 on the inside of the absolute value function, and then -3 on the outside. Well, on the inside of a function, when we're talking transformations, right, that's a left-right movement, and it's the opposite of the sign in there. So we're going to move to the left 2. So we'll take our vertex, move to the left 2, and the outside is normal. We'll go down 3. So we'll pop a point right, oop, that's too far, right there. Boom, beautiful, excellent. All right, so we went left 2 and down 3. Those are also my transformations. We'll write those down in a sec. So now the rest of this here is just going to be up 1 over 1 and up 1 over 1. Our slope is basically like 1. Since there's no coefficient out in front of the absolute value, just a slope of 1. We'll see something else on that second example. And I can go up 1 over 1 again if I'd like, do a few points, totally up to you, or maybe what your teacher requires you to do. All right? In the event that you're ever like, I'm not sure what I should do on this one, I don't know where the points should go, you can always make a t-chart. Check this out. So if I were to make a t-chart here, we'll say this is x, and then we got our g of x, so that's my output there. If I were to plug in -2, right, -2 is the point that I started with right there. I'll put that in the middle here, actually. If I put -2 there, -2 plus 2 is 0. The absolute value of 0 is 0, minus 3 is -3. And look at there, we've got ourselves the point -2, -3. If I were to plug in -1, I'll put that right over here, -1, well, I'd get -1 plus 2 is +1, and then the absolute value of +1 is 1, minus 3 is -2. And that's exactly what I got there. And if I plugged in 0, we'd have absolute value of 2, which is 2, minus 3 is -1. So if I put in 0 here, I would get -1. Beautiful. All right. Same would go on the other side there. If I plugged in -3, this would be the last one I do here. If I plugged in -3, I'd get -1 inside the absolute value, which is +1 when I take the absolute value. Minus 3 is -2. You know what? I lied. We'll do one more. Just to round this all out, -4 is going to give me -1. You'll see that symmetry going on there as well, as long as you find the vertex, that vertex which is right there, of that absolute value function. It's a good place to center your table. Again, table's not necessary unless you're required to do it, but it can paint a nice little mathematical picture for you in the event that you're not sure what to do with these transformations. All right, last thing on this graph here is our domain and our range. Just a common thing we're going to ask on pretty much every graphing problem. We're going to ask something about our domain and range, okay? So my domain here, well, my domain's all my x values. Does it ever stop going to the left or to the right? No, it doesn't. So that means it's all real numbers. X equals all reals. Or you can write that as -infinity to +infinity. Whatever your teacher might ask of you, I personally like the x equals the all reals because I like making that double stick R. I feel pretty dope. But interval notation, which is the -infinity to +infinity, works too. Okay? Next one. We got our range. So our range, let's see here. Does it ever stop going up? No. Does it ever stop going down? Does it have a low point? Yes, it does have a low point, which is -3. So you got a couple ways you could write this. So one way is y is greater than or equal to -3. I think that's the clearest way, probably the easiest for most. That would be the same kind of notation as this top one here. The other option is interval notation like we have with the infinities, and that would be from, hopefully we can still see here, I know I'm getting a little low on the board. We'd go from -3 to +infinity. Do we fit it? Pretty close. Just in case we can't see it, I'll write it right here. -3 to +infinity. All right, so those are the two different notations there. We'll just X that off. All right. Cool. Awesome. Wonderful. You don't need to provide both. This would be your inequalities. This would be your interval notation. Lovely. All right, next one over here. We got ourselves some fun, okay? Because we got a 3 out front. So, oh wait, did we write down our transformations? We did not. Oh my goodness, almost forgot. So for this one here, it was left 2, and then we went down 3. That was close, guys. Almost lost some points. Almost lost some points. Okay, now on to this one. Maybe we'll just write our transformations down right away so we don't forget. So the first thing here, that 3, that is a vertical stretch by 3. Some might call it like a dilation by 3 or a stretch by 3. It is a vertical stretch or dilation by a factor of 3. However you guys want to word it. I know some textbooks say dilation, some say stretch, whatever. All right. Next one here, we got ourselves a -1. So -1 on the inside means we're going to go to the right 1. So right 1, and then we're going to go down 5. Okay. So when we're graphing this, I like to start with my vertex, which would be at +1, -5. Okay, so +1, then 1, 2, 3, 4, 5, -5. Now, since we have that vertical stretch aspect, or that dilation, that 3 that's out front, instead of going up 1 over 1, we're going to go up 3. So up 1, 2, 3 over 1. And then up 1, 2, 3 over 1. Bada boom, bada bing. I'll connect my dots. You really only need 3 points on these to make it all happen here. On parabolas, which you haven't done necessarily yet, or maybe you're just reviewing, but the U-shaped ones, usually we want like 5 points. Here, 3 I think is fine, but your teacher may specify something else. Now, if you weren't comfortable with the whole seeing the 3 and blah, blah, again, we could do a T-chart, especially if they asked you for one. They might want you to fill one out. I'll show you guys how to do it. We got h of x right here. So my 1 was my x value for my vertex, and then I got -5 for the output, right? That was my vertex. And then I picked 0 as one of the points, and I also picked 2 as my other point there. All right, so if I plug in 0, I get -1. Absolute value of that is 1 times 3 is 3 minus 5 is -2. And as we saw, when we plug in 0, we do get -2 for my output. When I plug in 2 here, 2 minus 1 is 1, absolute value of 1 is +1, times 3 is 3, minus 5 is -2. And you see that symmetry happening there. It is going to be a symmetric graph over that where that vertex is, right? If I were to draw in a vertical line here, it's going to be symmetric over that. Cool. I like it. Vertex, boom, right here. That's the important one right there to get started. And then you can pick points to do a T-chart, or you can just use what you know about that 3 there, up 3 over 1. If it was a -3, it'd be going down 3, out 1. Okay. Domain and range. Domain, again, is going to be all real numbers. I'm not going to write both notations here. I'll just write the 1. And then our range, the lowest that it gets is at -5, so y is going to be greater than or equal to -5. There we go, guys. That's some dope stuff with our wonderful transformations here and absolute value graphs. Absolutely a blast, as promised at the start of the video. So if you guys liked it, check out more videos on these absolute value functions and have a great day. See you later.